Hello. So we're going live. And this is going to be episode 2 of the Building a Bioinformatics Project from Scratch series. Let me make a post on LinkedIn real quick. As we wait for more people to come in, I'm making a post on LinkedIn announcing this live session. And we're going to build a bioinformatics project from scratch, step by step. And today we're going to use a coding agent to retrieve the data and do some data preparation processing. All right, almost ready. So in the meantime, yeah, let me know, where are you guys coming from? Good question. Okay, so they, them, who ask how long would the stream be? I'm aiming for about an hour or so, an hour and a half. And yeah, I mean, feel free to join in, or if you missed some part, we have you could check out the live tab as well, or also drop a question after the live session as well. All right, almost ready. We have 7 people on the live stream right now. Yeah, so for those who just joined, we're going to resume episode 2 of the bioinformatics from scratch. And today we're going to use a coding agent. And let me get the link for you if you're interested in signing up for an account, or if you already have a coding agent, that is perfectly fine. You could use that. A coding agent like Claude Code, but then I'm going to use Cortex Code. And under the hood, we're going to use Opus model to run it. Okay, so I'm finding the link for you guys. All right, so I'm going to drop it in the chat. Yeah, awesome datum. All right, yeah, so I drop it in the chat. So this is a coding agent called Cortex Code, and you're gonna get like $40 of free credits if you sign up for that. But yeah, as I already mentioned, if you already have Claude Code or something similar, like Google's Gemini, CLI, feel free to use those as well. And yeah, let's begin. Let me share my screen. Feel free to ask questions during the session if you have any. Okay. So I think you're gonna see it. Alrighty. Yeah, so this is the coding agent that we're using today. So if you haven't already, check out the link that I provided in the chat. Sign up for an account and follow along. So while I'm going through, you could feel free to sign up for an account. And then once you have it, you could follow along. Or you could also watch the live stream again after it is completed if you haven't got the coding agent ready at the moment. But yeah, feel free to watch, ask questions as we go along. So whenever we want to launch a coding agent, we're going to fire up a terminal window. Like for me, I'm using a Mac OS X, so I'll type in Cortex in order to retrieve it. And if you're using Claude Code, then you could type in Claude. All right, and so now we have the agent ready. I'll just test it out, asking it hi, and let's see how it replies. All right, so it's now ready. So before we do that, let me take you to the ChEMBL API. So yesterday we essentially downloaded the data manually, but then now we're going to do that programmatically. Hey, Rafa09. Welcome. All right, so we're going to type in ChEMBL API. And then we're going to look at the API docs here. So this is the ChEMBL database, and this is the API version of it. And all of the functionality is provided here. Okay, so we're going to just provide this to the coding agent. So I'll copy it and then go back to the agent. So if you want the link to this, let me put it in the chat as well. And I'll also put it in the video description after the live stream has completed so that you could follow along. So we're going to now switch back to the coding agents. All right, so let's begin. I'll say I want to retrieve bioactivity data from, and I'll paste the link here for the target protein called aromatase. And then I think we should be good. But just in case, I want the KI IC50, PIC50, and pChEMBL values. All right. there you go. Oh, sorry. Yeah. So Rafa is asking, what am I doing? Awesome. Yeah. So this is episode 2 of the building a bioinformatic project from scratch. So in episode 1, I showed you how you could download a bioinformatic dataset from a database called ChEMBL. And today we're going to do the exact same thing, but then we're going to do it programmatically. So why don't I provide a quick refresher for you and for those who are just joining us. So yeah, let's show you. So this is the web service version or the API version of ChEMBL, where it allows you to retrieve the data, where the coding agent is able to communicate with this specific web page, and it will be able to download the data for you. However, yesterday I showed you how to do it manually, where we went to the ChEMBL database website here, and let me paste the link. Okay, so that link will take you to this particular page. And I wanted to use aromatase as an example. And if you're wondering what is aromatase, aromatase is a protein that is responsible for breast cancer. And we're, in order to prevent breast cancer or cure breast cancer, we want to find compounds or molecules that will be able to bind to the protein aromatase and inhibit the activity. So that's why we want to download the database or the data set on inhibitors, inhibitory molecule that will bind and inhibit the aromatase protein. Okay, yeah, cool. Rafa09. So you mentioned that my channel just appeared into your YouTube. Okay, cool. Are you doing any form of like data analysis or machine learning or even in biochemistry? So I'm going to show, like how you could essentially take a bioinformatic or biology data set and then use machine learning to build a predictive model. And then eventually at the end, we're going to have a data tool that will allow any user to provide the molecule and it will be able to predict the activity. So in a nutshell, we're going to pretty much do drug discovery, and it's going to be computational drug discovery. And you're talking about web scraping. It's quite similar, but then it's a bit easier than web scraping, where we don't need to go to the HTML page and kind of, try to use beautiful soup or something like that to retrieve data from the web page. But all of the data is already curated by the good folks over at ChEMBL. And we're going to just use their API to retrieve the data that they have already meticulously prepared, cleaned, and provided, curation service for the data. And we're essentially just going to download the data from their hard work. So yesterday I showed you how to do it manually, essentially searching for it, going to it here, and then selecting the one with the ChEMBL ID of ChEMBL 1978. And this is the single protein aromatase from the organism Homo sapien. Okay, so Rafa09 said you're a student of computer systems engineering. Yeah, awesome. Yeah, I mean, this could be like a side project that you essentially could build out using machine learning with coding agents. And a lot of the folks, like especially students, are asking me like, how could they get a job or be competitive in getting a job without having a job in the first place? Like without having like prior experience. And a good recommendation would be to build out projects on the side that you could, share to potential employer, and like building a machine learning project for a biology data set is something interesting that might be a bit more unique than the traditional toy data set, like the Titanic data set or the Iris data set, for example. Yeah, so now going back to the data, essentially we click here to see the entire bioactivity data. And then if you scroll here, you're going to see the IC50 value. You're going to see the exact value here. And then what is the standard unit? And what's the corresponding p-ChEMBL value? So, like this entirety here will be downloaded through the coding agent. That is what we're aiming to do today. So nothing fancy, just retrieving the data and then being like a programmatic alternative to the one that we did yesterday, which is here. So you're going to see that we have over 7,000 rows of data. And we're essentially going to focus on the single protein format, which is 3,400. And if we look for the IC50, let's see. Is it here? Yeah. So yeah, 4,400 are IC50. Ki is 641, which is what we're going to retrieve today, and also the PIC50 as well. And in addition to that, the IC50, Ki, and PIC50 will have an accompanying p-ChEMBL value shown here in this column. So what you need to do is just click here, the CSV button, and then it will generate the file, and then you just click on download file, and it will download it into your computer. So let me head back to using the coding agent. Alrighty. So our prompt was, I want to retrieve bioactivity data from, and then the URL of the ChEMBL API doc for the target protein called aromatase, and I want the Ki, IC50, PIC50, and the p-ChEMBL values. So this is what the coding agent is saying, and then we're going into plan mode. I'll just say yes, because it's asking whether I want to initiate the plan mode. And then it's going to do some research about the ChEMBL API in order to understand how to use it. Now, it's going to ask for permission to retrieve the information from the URL. I'll just go ahead and say yes, or always allow. And now it's searching for the aromatase. Oh, okay. Yeah, so Rafa is saying, I do not understand. Yeah, I mean, we're starting from scratch, so I'm not assuming that anyone will have any prior background. So, I mean, if you're interested in building out a data project that you could showcase as kind of like something that you do on the side that is quite interesting, I would say, that could potentially be pushed to your GitHub repo. And then when you're ready to do some internship or do some job search, then this will certainly be a good showcase of what you built using machine learning or AI. So it's gonna ask, what would you like to proceed with this plan? Okay, would you like to proceed with the plan? Let me look at the plan. So it has already explored the ChEMBL API, and it's going to use the ChEMBL 1978, which is the ID number of the protein called aromatase from human. And it supports filtering by target ChEMBL ID and standard type. Okay, that's good. The standard type will comprise of the IC50, the Ki, PIC50, as mentioned here already. And there's also 4,400 records for IC50, 641 for Ki, which matches what we saw earlier from the web page of the database of ChEMBL. And let's see further here. Key finding, p-ChEMBL value is a field present on IC50 and Ki, which is correct. I've also already mentioned that. So for each of the IC50 or KI rows, it's going to have a corresponding pChEMBL value column. And pChEMBL is essentially just, the IC50 or KI value, but then to the negative logarithmic to the base of 10. And so let's have a look further in the implementation plan. So it's going to write a Python script to do the following in 5 steps. It's going to query the ChEMBL API for the aromatase protein with the ID of ChEMBL 1978. It's going to retrieve all record for the standard type, correct. All right, it's going to load up 1,000 records per page. All right. It's going to include the pChEMBL value field. That is correct. It's going to save the results to a CSV file with the following columns, comprising of the ChEMBL ID of the molecule name, which is like the common name, for example, common name of the molecule. It's going to retrieve the canonical smiles. This is the most important part of the data. The canonical smile is a representation of the chemical structure of each of the compound. So it will look different. Okay, so let's see. Rafa09 mentioned that. Let's see. You're working on a platform with a coworker, and the platform is to analyze information, make predictions about parameters of a lake or something like that with a prototype sensor, with sensor. Okay, cool. Yeah, amazing. And so you're building a platform and you're using sensors to retrieve information. So same thing here. What we're doing here is instead of using sensors, these data are derived from experimental equipments whereby scientists have measured how well a particular compound are doing in inhibiting or stopping the activity of the aromatase protein. And they recorded the data. And then all of those data are published in the primary research article. And then the folks over at the European Bioinformatics Institute collected the information and kind of performed curation, like um, adding value to the data, kind of like scraping it manually and then putting it into a tabular form and making it clean for other scientists to use the data. And here we're just retrieving the data from their API. But yeah, I mean, similar concept, all data needs to be measured and then retrieved, consolidated into a tabular form, or if it's a structured information, and then we will use that structured format to do meaningful data analysis. All right, so I mean, everything here looks good in the plan, so I'm going to say yes. And now it's going to save the data into a CSV file called Aromatase Bioactivity. It's going to comprise of 5,097 records. And now it's going to perform the retrieval of the data. But yeah, something similar to what you mentioned about web scraping. All right, so fetch aromatase bioactivity data from the API. Yes, so let's just say yes here. So based on my usage of this coding agent, it's not doing anything disruptive. So in order to speed up, like instead of saying yes to all of the actions, sometimes I'll just press on Shift and then Tab, which will allow me to bypass the safeguard. It's only when you're absolutely sure that you could trust the agent to do task on your behalf. So yeah, it will run much faster autonomously without me having to tell it yes or no, you know? Okay, so Rafa09 said you're only in charge of the front end part of the platform, and that sounds pretty good. Yeah, that's awesome. And yeah, I mean, like, in order to be like a full stack developer, like the front end and the back end are pretty important. So side projects like this will allow you to kind of like have holistic overview of how to actually, like collect data. Like in this project, the bioinformatics from scratch, we're starting from, collecting the data, preparing the data, building a machine learning model, and then like analyzing the data, creating useful data visualization. And then we're going to build an app. We're going to build a web app using Streamlit in Python. And at the end, like you'll handle the entire pipeline from end to end. So essentially, it's an end to end machine learning pipeline. And we'll end with deploying a web app. All right, so it has already retrieved the data, and the KI here looks correct. And there are 5,000 records here. And if you're wondering why is there like 4462 out of 5097, it's probably because there are redundancy in the data, whereby the same ChEMBL ID might be present in multiple instances in the data. Because, like for example, an FDA drug might be present in multiple study, and therefore you're going to see multiple rows having the same compound with the same ChEMBL ID. Yeah, so we have 15 people online now in the live stream. All right, so let's see. Hi, Professor. I recently joined as a lecturer in a data science department and started following your work as it aligns with my research. Awesome, awesome. Yeah, that's pretty cool. Okay. Judging from your name, are you Thai? Looks like a Thai name. But yeah, I mean, congrats on your journey, career journey. It's really hard to remember all the syntax, what to do. Don't remember it. Just use it repetitively. And as you do so, you'll probably understand it and kind of remember it by yourself. Like, repetition kind of helps with that. Um, your thesis focused on epidemiological modeling for disease spread. Okay. And currently exploring how AI can enhance it, especially from a bioinformatic perspective. Yeah, I mean, epidemiology is probably kind of like monitoring population data at scale, right? And each data point could be, if it has geographical information, you could map it, right? And you're wondering how you could use AI. Well, AI as a coding agent will help you to do things that you might not have imagined before. You could have it, perform kind of like a literature review on your behalf, and it knows a lot of things. And you could kind of brainstorm with AI. So definitely use AI to brainstorm. Okay. Okay. You're from Indonesia. Yeah. Welcome. Awesome. Hello, Garcia. You're from Mexico. Yeah. Welcome. Oops. Gonna pop up with a new message. All right. So you're from life science background. Yeah. I mean, like most of the people watching here are coming from either a biology background or a computer science background. And bioinformatics kind of sits in the middle and it's perfect for both domains. So those coming from computer science might have some unique perspective about like how to analyze the data. And those coming from biology will have another unique perspective on, like the bigger implications of what the analysis might mean. And you might be able to link different chemical or biology evidence in your analysis. All right, so now we have the data, all right, and the data is located here. I mean, in my user working directory, and it has already, save it as a script so that I could reuse it for other target by changing the target ID, which is pretty cool. So now we're gonna do some data preparation. So things that I normally would do is we wanna make sure that we have a non-redundant data set. Non-redundant, we don't want any redundancy or duplicate. So we wanna deduplicate the data. Please create an Inchi key, because Inchi key are quite unique. Canonical smiles, I'm not sure. Sometimes the same chemical ID, the ChEMBL ID, might have different smiles. But yeah, I mean, Inchi key is quite definitive. So it exists only one Inchi key for a particular molecule. So we're gonna have it create an Inchi key for each molecule. And it's planning, it's entering plan mode. Let's wait for it. And while waiting, I'll answer some questions in the chat. Can you tell me the difference between bioinfo and computer engineering, computational engineering? Well, bioinformatics is a field that sits in the middle between informatics, computer science, and biology. There are similar fields like cheminformatics, immunoinformatics. It's just essentially changing the domain from biology to other domain like chemistry or immunology, or even geology, and then it'll be geoinformatics. So computational engineering, I think, is probably focused more on as the name mentioned, computational aspect of the engineering discipline. That could be like, buildings and thermodynamics and a lot of that, like computationally. Oh, okay. You were mentioning computational biology. Okay, yeah. I mean, most of the times these two terms are used interchangeably. Um, Bioinformatics and computational biology. But sometimes it seems that computational biology might have, in some circumstance, more. Yeah, I mean, rethinking it's quite synonymous. Yeah, so it depends on the person, but I see a lot of people using it interchangeably. But I like the term bioinformatics because it's quite easy. Like it's only one term, and yeah. But that's a good question. There might be subtleties. For those of you in the chat who knows, yeah, feel free to share. How useful agentic AI in computational biology? I think like nowadays we're in the age of AI agents. And what I'm showing you today is essentially how we're using AI agents to do tasks on our behalf. So instead of us having to manually collect the data, as we did yesterday in yesterday's session, now today we're going to do it programmatically, as we see here. We have already retrieved the data using the API from the ChEMBL database. And now we're going to do additional data preparation. And instead of having to, like manually code in Python all of the steps here, which could take days or weeks, right? But in using an AI agent, as you see here, it takes literally minutes to see it. And this works well for those who are less technical, as they are able to, like transform their thoughts into written code, and then the AI agent will be able to help you turn that idea, vague idea sometimes, brainstorm with the AI, turn that vague idea into more concrete code that you could, iterate through. So now we have zero duplicate activity IDs. Each row has a unique ChEMBL activity record. So there are 380 duplicate, but we won't remove all of the duplicate molecule. We're gonna keep some of them for the. Oh, okay, it's still running its task. So I'll just put in the prompt just in case after it's finished. For the duplicates, please perform. Please calculate the SD value of the SD50 KI and PSD50 and remove those having SD greater than 3. I think that should work. Yeah. So I already entered the prompt and now it's going to be queued for the next run. And as I'm waiting for this to happen, I'll answer some questions in the chat. So, Julian asked, could you tell me where would adversarial attacks arise in bioinformatics application and the need for robust or stable neural network architectures? Yeah, I mean, for those who are building more tailored machine learning solutions for the data, that would fit well for building a neural network architecture there. As for adversarial attack, it seems more like a cybersecurity topic. Um, yeah, that's an interesting point, but I'm not really sure about that. Definitely, if there's someone from the chat who might have some knowledge about that. But yeah, I mean that's some interesting take from you. Garcia's asking, some people say that a bioinformatist builds the tools. They have a strong math and programming background. Then there's a larger number of biologists that work with these tools but don't build them. Ah, yeah. That's a great take. Um, yeah, I mean, yeah, bioinformatics is, yeah, I mean, like for those who are more strong in the computational aspect, they are more inclined to develop tools that biologists could use, which is what we're doing at the moment. And for computational biology, they're potentially using computational tool to answer biological problems. But yeah, that's an interesting take. Thanks, Garcia. No, I'm using Claude Opus 4.6 for this. But definitely we could change it to other models as we see fit. If you're interested in using local AI models, there's the one from Olama. Yeah, maybe in a future live stream, I could show you how to use it. And Garcia corrected bioinformatician. Yeah, cool. Thank you. All right, so let's head back to the coding agent. So it's saying that for the SD to be greater than 3 filter, it should compute the SD on the raw standard value or on the ChEMBL value. Okay, sure. So it's asking me which should we use? Should it be the raw value or should it be the ChEMBL. I'll just use the ChEMBL because we're working across multiple activity types. Let's head back to the chat. But I know a professor of my, she does not code, but still produces bioinfo papers like sequencing, validating other more core researchers' data before they publish. Okay. Yeah, I mean, like sometimes professors in bioinformatics, they were coming from traditional experimental biology, and as their research lab grows, they hire postdocs, master's students, PhD students who are more technical or have coding experience, and yeah, therefore their team will have kind of like a team of people from various um, technical backgrounds, and therefore some will have coding skills. Yeah, that would be the case. All right, so heading back to the code, it's going to do the following. 670 groups have multiple ChEMBL value measurements. 2 groups have SD. All right, so yeah, so those have SD less than 3. And then 3100 groups have 0 or 1 ChEMBL value kept as is. Okay, so from 5,000, 3,000 have a single ChEMBL value. Okay, cool. And then the rest will be deduplicated. So the clean data will be saved here into the clean aromatase bioactivity.py. I mean, that's the script. And let's see. So the singleton is already in there. If SD is greater than 3, remove the entire group because, yeah, definitely because it has inconsistent data and it would confuse the machine learning algorithm. Okay, so let's do that. So let's confirm, and then it's going to do its thing. And it's exiting plan mode. Now it's going to perform the SD filter for us. And essentially, like if you're coming from a biology background or less technical and you have no prior experience in coding, AI agents will be able to help you to fulfill, like the coding aspect. So it's going to handle all of the technical coding for you. So it essentially you'll be able to expand upon your biology expertise, your domain knowledge, and take advantage of that to provide um, the coding on your behalf. So you're able to explore more um, computational ideas, even if you don't know how to code. From my LinkedIn profile, okay, you saw that I completed PhD in 2006 from non-computational field. Can you tell us from when did you start to pivot? Great question. So in 2002, I graduated my undergraduate in biology, and then I pursued a PhD in medical technology. In my second year, I started to learn machine learning at the time. I think data science is not really the the name that a lot of the folks in the tech field are aware of. It was called data mining. And yeah, so I started to use machine learning, started to learn MATLAB, started to learn R. And then it was only like after graduating PhD where I kind of learned and picked up Python. And so I graduated my PhD in 2006. 2000 about 2008, I learned Python, and then from then on, kind of used Python mostly for my research, and also R as well. But yeah, I mean, it took a while, and I kind of stumbled upon Python later on in 2008. And so it's been what, 18 years now using Python. Okay, Rafa says you're gonna pass on the last class and then pass it to Notebook LM. Yeah, that's a cool take. All right, it's finished. Let's have a look. All checks has passed. Let me close out the task. Done. Here's the summary. And then 2 groups removed. These had wildly inconsistent IC50 measurements. And now we have these. So these groups, meaning that they are duplicate compounds, and we're going to deduplicate them, where we're going to take one of the duplicates and then use it. So yeah, let's say it might have, let's say that it started from 2000 rows, and there are 668 unique molecule in there, and we're going to deduplicate it. So from 2000, we get 600 something molecules. And now the final row count will be 3,774. Unique molecules will be 3399. Inchi coverage 100%. And let's see, by type, awesome. Okay, cool. And the new columns added were the SDP ChEMBL and the N measurement, because each duplicate will have the number of measurement, like how many molecule are in each duplicate. Like some duplicate could have 10 rows, some duplicate could have 5. And it added a column for the Inchi key. Awesome. So now we're, like essentially we're doing the data preparation to ensure that our data has high quality as much as possible. So we have already removed the redundancy in the data. Now we have a non-redundant data set. Um, so I'm kind of, thinking about this as I go along, looking at what we get from the coding agent, and then kind of figure things out along the way. Okay, so let me check the chats. Can Let's see. Can you tell me if all of these like R, Python, MySQL are all needed for ML, or should I stick to one? If you're starting out, I would recommend stick to one, and as you become more confident, then you could branch out to other technologies like MySQL if you're dealing with databases. But definitely, SQL is going to be pretty important as you work with more data. And then you mentioned that you didn't know that something like ChEMBL existed. And yes, there are a lot of databases, in biology where they collect data and kind of perform data curation. Um, I think I wrote a review article once. Let me see if I could share that with you here. Let me recall, what is the name? Reproducibility, computational drug discovery. All right, I found it. Okay, let me share the screen. So this is a review article that we wrote. We as in yours truly and several others. We have Professor Matthew Paul Gleason, we have Professor Ola Spute from Uppsala, and then we have Nalini and Saul, who were my postdoctoral fellow and master student in the program. And so we wrote about, I mean, you could also look at the same one in the publisher's website. So here it is. So this is about the reproducibility and computational drug discovery. And I think it was a timely review article, which is pretty new in the area at the time. So that was like in 2020, just a year before I kind of quit academia. So we kind of reviewed about how we could achieve reproducibility in computational drug discovery, about like documenting research, about um, putting all of the like cheminformatic work in a Jupyter notebook so that you could essentially share it on GitHub's repo. And yeah, there's several other topics that we also covered in this review article, and it's free. You could read it for free. It is open source. I mean, it is open access. So you could download this and read it for free. So let's head back. All right, so now that we have the data, I think we're in a good state. Now we're gonna have to compute the molecular descriptor. Um, let's use molecular fingerprints. Can we compute? Let's use interpretable molecular fingerprints for this data set. And let's see how it will kind of brainstorm and provide suggestion on how we will go about doing that. So a lot of the research work that I've done previously was using descriptors that are interpretable, meaning that it will allow biologists and chemists to be able to figure out what is the important features from the machine learning model that we've built and which feature will pretty much govern the biological activity. And therefore, it will provide some actionable feedback to the biochemists so that they will be able to refine the molecule or go back and design better, more effective compounds based on the insight that we got from the machine learning model. So let's have a look. What is going to do? Essentially, it's going to use RDKit and it's going to use the Mordred package as well. But typically, I'd like to use more like PubChem features, PubChem fingerprints, and I think it's available from Paddle software. And there are others as well from the CDK package. So these molecular fingerprint are accounting for the molecular structure of the molecule. An example fingerprint could be like, does the molecule has a carbon atom? Does the molecule has a hydroxy atom? And if it does, then it will have a number of value of 1 or 0. So it's binary. And essentially, you're going to have like a couple thousands of fingerprints. And each molecule will have unique fingerprint because each bit or column will represent the binary on-off of each of the fingerprints. I mean, each of the molecular features. So it's gonna suggest me that it's gonna use max key RDKit to the descriptor Morgan. Highly interpretable. Okay, max key sounds good, but let me see if it's able to do this. Let's see, one moment. Can you compute PubChem fingerprints? And I'll say next, submit. And yeah, I mean, it's able to figure out that it might be in Paddle So that software, I mean, that package will have the ability to compute the PubChem fingerprints. And from my previous papers, we use PubChem fingerprints for most of the interpretable model. But there are several other fingerprints as well that we also compared that to. Cool. Yeah, but then the downside is that it is Java based, so it might be pretty slow for the computation. Okay, so now it's going to perform the calculation. Wow, it's gonna do 5 seconds per molecule, 5 hours. Maybe not for this session. Yeah, we need something fast. We'll just use max key for now. All right, so we're gonna save the PubChem implementation for later, and we're gonna compute the max key for now. And let's see how it goes. Oops. So now it's going to calculate the max key. It's going to be fast. That's great. Millisecond per molecule. All right, so let's do it. So the non-redundant dataset will now comprise of 3,774 rows. And that's going to compute the fingerprint. Yeah, so what I'm using is called Cortex Code. It is a coding agent, and it's from Snowflake, and Snowflake is an AI data cloud platform. So it handles the data pretty well. Oh, cool. Yeah. Read the paper. Yeah, that's pretty cool. Yeah, I mean, we spent a lot of we did a comprehensive review on the reproducibility in computational drug discovery. And yeah, I hope it will be helpful. You want to become a data scientist and you wasted 5 years and feel like you can't become a data scientist. Um, yeah, I mean, like, sometimes waste could be subjective. Maybe you are in the learning stage, and sometimes progress that is not apparent. So it might not be, um, as clear as you want it to be. But keep on grinding, work towards building your data project portfolio, and I think you'll be able to, in due time, if you put the time, effort, and build out your portfolio. I mean, anyone could become a data scientist. So yeah, go for it. So now it has already computed the max fingerprints, and let's what should we do next? Let's build some models. Maybe compute another fingerprint. Let's see. What other interpretable fingerprints can you compute? Okay, yeah. Fingerprint PubChem, but I think it's coming from PaddlePie. Yeah, right here. PaddlePie, but it might be slow. Yeah, I really like these three descriptor, but yeah, it's pretty slow. Yeah, maybe let's use the ECFP4. Yeah, let's compute. So what about we see if it could build a native Python version for us without, like the Java implementation? Would it be that capable to do it? That might be interesting. So let's while it's computing, let me answer. Let's see if there's any question. I'm currently studying DSA and C++, and it seems like professors all over the place, and I can't find any in-depth mathematical tutorials for time complexity analysis. Do you know of any? That's an interesting question. I'm not really sure about that. Time complexity analysis, but I'm sure there are resources available online, and you could definitely brainstorm with AI to help you find some additional readings. Yeah, I do that all the time when learning new technology or algorithms. I'll brainstorm with AI and have it suggest, or even like do a preliminary literature review on my behalf and kind of summarize papers for me as well. Yeah, interesting question. Cool. We now have ECFP4. Let's see. Can you convert paddle pie from its Java implementation to a native Python um, implementation so that it runs much faster? Let's see what it does. So no hope. I mean, I don't expect anything, no expectation, but let's see if it is able to do something amazing here. Significant undertaking has better solution. PubChem fingerprint. Okay, so it's finding out one paddle is slow, it spawns already kits already done, runs in millisecond. If you find a smarts pattern, we can implement them directly in RDKit using smarts matching. Oh, that's interesting. It could do that. Native RDKit based PubChem fingerprint calculator. Yes, let's do it. So it's going to use the smarts pattern, and smarts pattern are essentially kind of like a pattern of how a functional group or a combination of atoms look like. And it will use that pattern to do the calculation. So let's see if it works. Let's see if it's able to do something like that. I mean, that would be a very great time saver for a lot of folks wanting to compute this descriptor. So it's going to look at the PubChem fingerprint here. Okay, I have a question in the chat. Was your VSC 4 or 3 years long? Mine was 4 years long, and in my fourth year, I did the undergraduate research project where I spent about a year at the beginning of my fourth year to do some investigative work. It's more biology in nature. So what I did was I would, in the morning, go to a pond in the university to collect information from about the migration of copepods. Let me put it in the chat. And I'm looking at the diurnal migration, meaning that in the morning and also at night, how is the migration of the copepods change across the day and nighttime? and then essentially I'll collect the number of copepods from various depths of the pond, and then I'll take it back to the lab, and then I'll actually do the count. So I have a counter, and then I have a forcep, and then I'll just put it into alcohol and kind of count it one by one. So it took a lot of time. So most of my research was essentially collecting copepods from the pond and counting the number at the various depth of the water, and also from the morning and at night. So that's like a couple months, collecting the data, and then use SPSS to do the analysis. And yeah, that's like my first exposure to doing scientific work. But yeah, I mean, that work kind of got me the opportunity to attend a research conference for the first time in Taiwan, and we presented that, and I was able to meet some pretty important field people, researchers, professors from the field of copepods at the conference, and yeah, it was like a pretty amazing experience, and that kind of got me interested in wanting to pursue more, um, research in a more extended form. So that kind of eventually led me to do the PhD. And that took about 4 years to complete. So let's head back to the coding part. So here we have, all right, write a script, hybrid approach. Rather than rewriting all from scratch, you'll convert all Unix files to a single SDF file using RDKit. Run paddle on the SDF, extract the column, merge it back. I'm not sure. Let's see. After researching element found, refer to implement using atom counting. These are defined in the CDK and require extracting, translating. Okay, so it seems to be much more difficult than it originally anticipated. Oh, and it says like this batch mode would be easy. Okay, so it did some confirmation. And it's saying that this hybrid approach might be taking 4 minutes. Okay, let's do it. All right, let's go back to the chat. Okay, you're saying you're from an awful university. Oh, sorry to hear that. They won't even let us do research on our final year. Even if we graduate, we wouldn't have any projects under our belts. Well, could you do it in your spare time? Yeah, then definitely, I think doing side project would be a good way to explore this. And if you're able to, like during the summer, reach out to some universities and see if there is any research opportunity, like a short project that you could potentially join. I do know that like some of my peers, they reached out to universities even beyond Thailand to work in US for like 3 months for a project, but then they won't provide any support. So essentially, all of the financial expense, the student will have to handle all of that. But yeah, I mean, it was a pretty good experience for that friend of mine. Hey, AJ has joined. Welcome. Yeah, so today we're running the coding agent to retrieve the data for the aromatase inhibitor, and we're now in the stage of computing the molecular fingerprints. And now I'm trying to see if I'm able to use PubChem fingerprint and see if we could, create a better version than the PaddlePie one, because PaddlePie uses Java and we want to have it more native implementation in Python so that it runs quicker. So essentially, we're doing that right now. Just taking some time for that. And you'll see that it's now, performing the task and is at one of three steps. You essentially could, press on Option and T at the same time to looking at the task it's working on. So first step is write the script. Second step is run the script. Third step is verify output and cross-check against known values. And then you could press on escape key to return back to the session. And yeah, definitely you could do research from your side. So in spite of the limitation that you shared, I certainly think working on a side project like this, what you're seeing in this live session, could be a good step that will allow you to have experience doing concrete research. And as I mentioned in the previous live stream, our aim is to publish a research article for this project. And for those of you who want to contribute to this ongoing research that I'm doing right now, I might consider having some as potential co-authors in the research article. So that would be a good experience that you could definitely include in your resume or CV as you kind of figure out what you want to do next in your career, whether that's working in industry or doing a PhD, master's, or yeah, additional various other career options. So let's head back to the coding agent. Let's see how it's going. It's completing the run and it's done and verified. Okay, that's interesting. Okay, so we don't want, I don't want to have it all in the same CSV file. So now it's saying that it's able to compute the PubChem fingerprint and it's able to do so in 3 minutes, less than 3 minutes for the 3,400 molecules, but the paddle implementation would have taken 4.7 hours. So it turned 4.7 hours into 3 minutes. And you saw that we developed this live, and this is pretty cool. Let's see. Let me ask it, did you verify some of the molecules in using the Java-based paddle implementation and our newly created implementation? Let's see if that works. I mean, if they have already done so, it seems to have did the check here. So I'm going to compare the batch SDF-based paddle output against the original paddle output. Okay, let's see if that works. So originally, it seemed to did the check on only one molecule. Let's wait for it to complete the check and verification for us. Okay, so let's see. We have a question from the chat. Okay, we already answered that. Yeah, that's a good question. Yeah, so the topic of the research is that we're doing is the quantitative structure activity relationship of aromatase inhibitors. And essentially, we're going to build at the end a machine learning prediction tool. and using Streamlit. And yeah, today we're collecting the data, preparing the data, computing the molecular fingerprint. And in following live streams, we're going to build the machine learning model. We're going to do some feature selection. We're going to maybe run some hyperparameter optimization. And then we're going to write the research article. And yeah, we potentially will use AI to help us write the article, but not, purely relying on AI, but we're going to use our human intuition to improve the article there. And ultimately, we're going to publish the article. So we're using AI as kind of like to assist us in performing the task that we would normally do, but that would take maybe several months. But then we're going to compress that into maybe days or weeks. So yeah, AI at scale. So it has performed tests on 5 molecules, and some had minor differences while others have exact match. Okay, that's interesting. And I think we could definitely iterate this. So please summarize our concept to an agents dot. Okay, let me first make sure that we have all of this in a working directory. Please store all of these project files in a dedicated working directory called Aromatase. Because right now it's just storing it probably in my user working directory. Yeah, so originally it was probably in user chenin, and now we're going to store it in user chenin/aromatase. Yeah, so we're going to put it in the aromatase subfolder. All right. So all of it are now in the subfolder. All right, cool. Now we're gonna please create an agents.md file to store what we've done so far. So the agents.md file is essentially kind of like a memory file, or a rule file that we give to the LLM or AI in a future point in time. So it provides them with additional context to what is the current state of our project so that we don't have to explicitly remember where we left off. So AI will be able to write, the current memory into a file, or the current rule and preference that we like, or how we perform a certain thing into the file, so that in a future point in time, the AI could make reference to this agents.md file. Please save our potential improvement opportunity of the Python native implementation of PubChem, FP, and substructure FP, and what's the other? Rod FP. So we want to implement that maybe in a future point in time. So we want to save our progress there. Okay, so now we have already implemented PubChem FP. Can you improve on the PubChem FP? There were some minor inconsistency with the native PaddlePy. Let's see if it could do that for us. Now is going to run the fix. And like when you're working with AI agents, you're not limited to one session. You essentially could run multiple instance or session at the same time, but you have to be aware that it will consume more tokens or cost. It will cost you more. So yeah, take that into consideration, but you will be able to complete the task if you're much quicker if you're able to work on it in parallel. So typically, like for me, I might work in parallel like 5 or 6 different windows, and then it's gonna run as task. Typically, I package it so that it will be able to run it in a batch, which would take considerably several hours for it to complete, instead of me having to be the human in the loop to approve the changes. So typically, I'll do the plan mode so that I know that what the AI will implement will be as I would expect it to be. And so the AI will be able to implement that in one shot instead of having to iterate through with me. And so that's going to save my time. And as a result, I'm able to work on multiple aspects of the same project at the same time, and that will greatly help me to complete the project much faster. But yeah, I mean, as we're going through the tutorial here, step by step, we're focusing on a single session, so that for those of you who are new to the concept of AI agents for coding, you'll be able to follow this easier. So let's see. We have some questions in the chats. Okay, you're currently looking into the function of aromatase enzyme. Yeah, I had a review article about this as well. Yeah, feel free to look up aromatase and then my last name. We have a few research article, or you could just search for aromatase review, and you'll be able to find some review article about aromatase. And yeah, our research group at the time did a review article on aromatase as well. Yeah, I mean, everyone has to start from somewhere. So yeah, don't worry about that. In due time, you'll be able to have more knowledge about it uh, as you read up more about it. Yeah, okay, that's cool. Yeah, you're making pretty good progress here. Yeah, aromatase, it's not like the smell, but it's for efficient biosynthesis, as you mentioned. Awesome. Yeah, cool. So now it's gonna do the fix on the ring part. And now I think it figures out how to do it. And as you'll see, it's working autonomously to provide the fix for you. So you'll see that AI has a lot of capability, but then it still requires some human, like intuition for it to perform its task well. So sometimes you're able to provide that additional insight for the AI in order to allow it to dig, to get unstuck in a way. It might get stuck in a trench, and then you kind of help it to get unstuck. But yeah, it's pretty cool that we are able to kind of work together with the AI, brainstorm a little bit, and try to see different angles of it, and have AI perform the test on your behalf, and then you know implement this native and more quick implementation. So it's found the bridge bond and it's recomputing. That's cool. And I have another computer here that I'm running on the side. Okay, and this one has already completed. Okay, now I'm back here. So we're still running the implementation of the fix. And it's found that the issue is something to do with the length of the ring bonds. Okay, let's see. I have some more questions in the chat. Will you be posting more videos for the bioinformatics video you made about 1 year ago? Yeah, so we're actually, like I wanted to, package the video into a more refined way, but then video editing kind of, you know, takes time, and doing the live stream is a more viable approach at the moment. I know that some of you might be following on the bioinformatics from scratch tutorial, and you might see that I haven't really been posting videos there because, yeah, my full-time work as a developer advocate is getting pretty intense. Um, we have a lot of interesting project that I'm working on, and yeah, recently I was promoted, and yeah, more responsibilities, and therefore I'm trying to figure out ways on how it could be more consistent on YouTube. And yeah, doing the live stream seems to be a good approach, as I'll be able to you know be more consistent. And then definitely I think we could maybe do some light editing on the live stream and maybe reshare that, to continue the bioinformatics series. Yeah, I hope that this live stream is more authentic. You'll be able to see all of the errors that I see and kind of figure out how I debug the issue. And now with the help of AI agent, it has been becoming so much easier. Let's have a look at the steps that it's working toward. So it's at step 1 right now, and there is a total of 4 here. And then it's going to compare with the original implementation. That's cool. Awesome. Yeah. So this live stream is actually a more extended part of the bioinformatics from scratch series. And in the last live stream yesterday, we completed episode 1, which is how to retrieve the data manually. And today we're doing it programmatically. So today's episode 2. And our ultimate goal is to publish a research article. And so we're gonna work our way towards that goal. And in between, we're gonna, build the model and then create the data app for the prediction of the activity. Yeah, so the live stream would take more time, so to say, to watch through. And the more refined version would be like a highly edited version, so that takes less time to watch and follow along. But yeah, I mean, if I have more time, I try to see if I could record the more refined version. But I hope that the live stream will provide some value, especially for those wanting to complete the project, because as you'll see, I think I released 2 episodes last year. Awesome. Yeah, congrats. Yeah, thank you so much. Would love more live stream. Yeah, that's awesome. Thank you. Congrats. More congrats. Thank you. Yeah. Let's see. Back to the coding part. All right, so it's updated. Now it's gonna regenerate the fingerprint file. Now update the cleanup section to remove instead of SDF. Okay, so I think it's completed. And it says that it now has 5 out of 5 perfect match. The fix is simple. Use a smiles file instead of SDF. This avoids the RDKit to SDF. Yeah, because when it convert the smiles, which is 1 dimension, to RDKit to the SDF version, it's 3 dimension. Therefore, it introduces more, more issues to that because of the 3D information. Okay, so it's updating it now. So let me provide the AI with additional instruction as a queue for it to run after it completes this one. So I'll tell it to please make sure to separate the calculated fingerprints as an independent file, CSV file. Make sure you add the molecule ChEMBL ID as a unique identifier of each row. No need to, okay, let's see how it does for that instruction. Let me check up on my other work here. All right, so the other work is running. Let's go back to the chat here. How many live streams do you think this will be? I really want to do this project too. I'll try to catch up. This is my first live stream. Yeah, so this is the second live stream as part of the Bioinformatics from Scratch series. So make sure to watch the previous live stream, and it's created as 3 separate parts. Actually, it's the same episode, but then there was some technical issue with the internet, and therefore it was split into 3 different parts. And I have already named it as episode 1, part 1, episode 1, part 2, and then part 3. But yeah, I'm not sure about how many streams that we're gonna do. I'm thinking probably maybe, I don't know, in the range of 8 to 10. We might have complete the entirety of this, but yeah, we'll see as we go along. Because for future live stream, we'll have to take what we built today, which is the molecular descriptors, and then we're gonna do the actual machine learning model building, and then we're gonna interpret the model, and then maybe we'll do some hyperparameter optimization, and benchmarking it with several other machine learning algorithm, and maybe doing some machine learning model stacking to improve the performance. And then after that, we're going to do some feature importance. We're going to interpret how features contribute to the activity. And we're going to create some pretty cool data visualizations. And then finally, we're going to create a prediction tool in the form of a data app. And then we're going to deploy that publicly on the internet. And then, only then, we're going to work on the research article. But yeah, at every step of the way, if those of you in the live stream would like to help out and independently run some additional work that could contribute to this, maybe I'll create a GitHub repo that will allow you to contribute to this project so that you'll be able to, take part in it. And if you provided meaningful contribution to the project, I'll also consider adding some of you as co-authors to the research article. So yeah, it's going to be a pretty cool community-built project that I believe no one has ever done before. So this is going to make history, and you'll be part of this. So let's see where we are now. Okay, so it's adding everything into the same file. So my next instruction for it is to separate it into distinct files. Yeah, okay, I think I shared the wrong one. Okay, that's awesome. Yeah, please do, please do. So in future live streams, I'll probably create a GitHub repo that will share all of this publicly. And yeah, I mean, that will provide you guys with opportunity to contribute to this ongoing project. So I think for today's live stream, we did a lot here. We programmatically retrieved the data of aromatase inhibitors, and then we perform de-duplication of the data in order to get the non-redundant data set. And then now we are calculating the molecular fingerprint. And as we noticed, the PubChem fingerprint would have taken several hours if we were to use the original implementation from PaddlePy. Then we're creating our own, and then it's validating the correctness of that. And it has essentially reduced 5 hours to less than 3 minutes for the calculation. So yeah, that's pretty cool progress that we have so far with the AI coding agent. Only person you know to try something like this is so exciting. Yeah, I'm glad that all of you are joining in on this initiative here. This is kind of like a classroom, like a virtual classroom that we have on the internet. But yeah, definitely contribute to the project as it goes on. And I'm glad that you're excited for this research project. Let's see, what is the progress? It's still running. It's generating the file. Let's wait for that to complete. And with AI coding agents, like as you see, we are creating a more enhanced version of the molecular fingerprint calculation. And I don't think there's a limit that we can't do, right? There's essentially a lot of ideas that will be able to go from an idea to an implementation here. And the other day, I was working on a new Python library that will allow you to visualize um, information in three-dimensional. If you might have heard of Obsidian, it's going to be something like that, but in 3 dimensions. So you could rotate, kind of like the galaxies, right? You'll be able to see the stars, and each bright star will be essentially a molecule, or essentially could be a document that you have in your computer. And it's going to be located, I mean, each data point will be grouped by the similarity. So if it's similar, it'll be grouped closer together. If it's different, then it'll be further away from each other. So yeah, that tool will be pretty general purpose. We could use it for representing knowledge, or even the notes that you have, like your second brain, so to say. If you create multiple markdown files, create your second brain, and we're able to visualize that all of that information, or even create a three-dimensional chemical space, and you'll be able to visualize that. I know that you could do it using Plotly for a three-dimensional scatter plot, but then we're gonna embed that into a Streamlit apps that the user will be able to interactively, like look at the molecule, look at the research article, or any notes that you've taken in 3 dimension, and maybe have it suggest some potential connection of each molecule or information, and see if it could generate some new areas that might be interesting to explore. But yeah, that's something exciting that I'm working on, a new Python library. So yeah, I might share that with all of you in a future live stream. So okay, so still working on it. almost, I think it's almost finished. We're almost at 2 hours, right? An hour and 40 minutes so far. I think it's almost finished. Let's see the column count. And it's working on the next prompt that I provided. Let's see if it is able to do so. We're gonna split this massive single file of a CSV into the original CSV file, the PubChem fingerprint file, the other, the max key CSV file. Okay, it's able to do so. So we have the bioactivity curated. I'm not sure what is this. Oh, okay, it's the combined file. Let's remove the combined file because it's redundant. So when we're building out the machine learning models, we're gonna take the Y variable or the IC50 or ChEMBL value from the curated CSV file here. And then we're gonna take the remaining fingerprints from each of these files. So now we have the max key file and the PubChem file. Can you show me the first 5 rows of these files? So we gotta do a check. Okay, so let's see. AJ has a question. I use CodeLab. When does Snowflake make more sense? Well, like as a single user, learning out, especially if you're in university, candidly, like CodeLab is pretty fine for what you're doing. But then if, let's say at the university level where there could be multiple research group, or if you're working from a big laboratory, having Snowflake would make sense because everything is already on the Snowflake platform. Um, but a disclaimer is that I'm currently working for Snowflake as a developer advocate for Streamlit open source. So I use Snowflake, and also the Cortex code here is also created by Snowflake, and it has some systems prompt built into Cortex code that allows it the ability to allow you to do a lot of data task that traditionally would have been difficult for the LLMs. So as you'll see here, we're able to do this. I mean, of course, Claude Code will be able to do it as well. But then when you're ready to kind of deploy it to the cloud, you could do so using Snowflake. And yeah, I mean, like kind of generate the data table on Snowflake, and you could ask it in natural language, and it will be able to do so, or even deploy the machine learning model to Snowflake, and then having observability to the machine learning model and having a API REST API version of the deployed machine learning model ready, and also deploying the Streamlit app to use the REST API from Snowflake directly, which is much easier to set up than stitching together multiple tools. So you work with only one platform, and it does everything for you. It's like consolidating everything into one place, which makes it a lot easier to work with. But yeah, I mean, s- for students, I think Colab is more than enough for you to run the projects. Yeah, so that would be my take. Yeah, awesome. Glad I could answer. All right, we're finished here. So first 5 rows of the file, I think it's showing here, so but I couldn't see it. But let me check out the. So I'll create a. Would that work? Okay, so So I create a new tab, but it's not updating. I might have to reshare the screen again. Okay, so I'm going to go into the so these are the files. So I want to have the AI to help me. But before doing so, let's take a look at the data file. So we have the clean data, we have the curated, and we have the fingerprint. Let's have a look at the fingerprint here. Okay, yeah, this is how a fingerprint file looks like. So we have the ChEMBL ID, and then we have all of the fingerprints here. Let's look at the top part, head 5, or even just 3 for the molecule. So these are the first row. These are the name of the PubChem fingerprints. And then we have the ChEMBL ID here. Okay, it looks correct. It's not empty. We could even do this. Let it do the cat. So cat will essentially print out everything, and then we could pipe it to word count, the number of lines. And we see that there's 3775 rows of data here. So yeah, knowing a little bit of the command line prompts would be good to investigate the data files here. And let me go back to the coding agent, and I wanted to organize the file so that it looks good, because currently there is no subfolders in here. And let's add some structure. Okay. Oh, I need to change the tab first. Okay, let me do it again. All right. Can you organize the files for me? Create logical subfolders like scripts, data, etc. Let's see if you could do it for me. So we have 13 files in total. Okay, so it's creating it. It's going to clean it. So it's putting the Python files into the scripts subfolder. And let's see if we could do the same for the CSV files. And it's even correcting the relative paths of the file, I believe. So it's doing a thorough check for all of the files. And it's updating the agents.md to reflect the new structure. That's good. Because, like every time when you run something in AI, in the prompt here, the AI or LM will check out the agents.md file for context. And it's reading and editing the file again. Let's see how that goes. So it even has a reproducibility section. And yeah, this is the overall structure of the folder now, which looks pretty clean. We have the agents.md at the root of the folder. We have the script subfolder, and we have the data. And the data even has a further subfolder called raw and the processed and the fingerprint. Super clear. Yeah, because I wasn't sure like what's the difference between the bioactivity and the bioactivity clean here. And so this makes it much easier to comprehend. And it has already saved that all of that information into agents.md. Yeah, so we essentially did the calculation here. Let's calculate one more fingerprint. Let's see. How about the substructure FP? Can you create a native Python implementation? Let's see if it is able to do so with the substructure FP. And even, like I think I probably will create a new Python library to share the new molecular fingerprint calculator for these native Python implementation, which is much quicker. I think like what from 5 hours to 3 minutes is a lot of improvement there. So I think it will probably be helpful for other people looking to calculate this descriptor. So it has the full smarts pattern file, and it's gonna look at the patterns. Cool. We're gonna do the same thing, but then for the substructure fingerprints. It's encountering some issues, and it is debugging by itself, which is pretty amazing. It mentions that the file was truncated, so it couldn't see the entire file. So it's gonna try to figure out how to see the entire file. And I think it solves the issue here. And now it's gonna read the contents of the file. Okay, it discovered that there's one invalid. RDQ doesn't support but can be implemented. Okay, and it's now implementing it. It's pretty cool. So it's figured out that Paddle uses an XML file to compute the fingerprint, and now it's gonna try to make sense of that XML file. So it says that, yeah, it's summarizing what it has done. And it seems that the final bit here on salt is having an issue. So it says that it takes 3.8 millisecond natively versus 91 millisecond with paddle. So it's doing a 24 times the speed up, and there's no dependency on Java, which is cool. So it's going to take 13 seconds versus 5 minutes if using the Java version. So that's a significant speed up. And now it's going to check whether the ordering of the bits of the fingerprint is matching the original version. And now it's comparing our implementation versus the paddle implementation. And so it says that there are some differences, but it's natural. Okay, so it's giving us a plan, so let's do it. So you'll see that the AI kind of investigates the issue, did a background search here, provided the steps that it's going to do for the implementation and how it's going to verify that. And then we essentially just confirmed the plan, and now it's going to do the implementation in a single shot. I think it's pretty cool. And here there is multiple steps of 5 for it to do. Now it's performing step 1. So it has a total of 307 columns or fingerprints. So it's going to create the script now. It's going to follow the same structure as another script file. And now it's going to run the calculation on the implementation here. Let's see. I think it should take a few minutes, as it mentioned. Is it 3 minutes? Yeah, I think it's probably about 3 minutes. Oh, wait. 17 seconds. Oh, okay, 24 seconds. It mentioned about 24 seconds. Now it's done in 17 seconds. So the check is done, and now it's going to do some cross-validation. 98.9% overall agreement, 3 to 5 bit differences per molecule. All in the expected aromaticity sensitive bits. Okay, but then, there are some minor inconsistency. So I think we should definitely give it a fix. So it's updating. Okay, good progress so far. All right, it's updated. So I think it's completed. Let me mark the final step done. Awesome. But we definitely should fix it, right? There were some inconsistencies. Can you fix it? So it says that it's not a bug, but a known RDKit versus CDK aromaticity difference. So there's a total of 1, 2, 3, 4, 5, 10 bits out of 307 that had some inconsistency. So now we're going to fix it. So it's what, 3%? Let's check the question out. Okay, so the question is, what approaches do you find most practical for identifying when a QSAR model is predicting beyond its chemical space? Great question. Typically, I do a applicability domain analysis. So that will tell you whether your molecule, the new molecule that you're trying to use to the one that was used for the trading set are in alignment, whether the new molecule has similar chemical space. Does it fall in the same chemical space as the one used to train the model? If not, then you're able to say that the new molecule is beyond the applicability domain of the existing model that was built. Yeah, so applicability domain would be a good way for you to evaluate whether your compound is predictable using your trained machine learning model. Hope that answers your question. So I think it fixed the issue, right? So the fix is the same approach we used for PubChem. Now it's updating it. That's cool. So it's going to use with Spile's input. Okay. We definitely should tell agents.md that the fix is using Smile's input to paddle. Let me make note of that. All right, so it did a check and it verified that 5 out of 5 are exact match between the implementation that we had and also the paddle pie. So that's great. We were able to fix the substructure FP, and definitely, I think I have another idea. I'm going to create a Python library that will provide all of this native fingerprint capability. Can a model have strong metrics but still poor applicability domain coverage? I think anything goes, definitely. That could be the case. So definitely, I would recommend also calculating the applicability domain of the model as well, because there's always a thing called model drift, and the model will not be applicable if the data from a future point in time has significant shifts in the chemical space. And, like with great advancements in chemical synthesis, it also confers the ability for medicinal chemists to synthesize new compounds that might not have been possible in the past. So therefore, the chemical structure and the chemical space would then evolve over time. So a model built from 10 years ago might not be applicable to model to some recent molecules that are being synthesized. So the model needs to be updated so that it is current to match the ongoing evolution of the chemical space. All right, so we got it fixed here. So let's see. How many CSV files we have for the FPs? So we have the max FP, we have the PubChem FP, and we have the substructure FP. Awesome. So now what's remaining is the ROT FP, ROTH, which I think we could do in another session because it's getting pretty late now. It's 1 a.m., a little over 1 a.m. in the morning. So I think I'll call it a night. And as a recap, today we've learned how to programmatically retrieve the aromatase inhibitor dataset from the ChEMBL API doc. We've also removed redundancy in the data, so we performed de-duplication of the dataset. We also computed some molecular fingerprints to describe the structure information of the compound. And so far we have 3 molecular fingerprints calculated, and we're gonna do additional calculations in the next live stream. And then all of the links API doc link I'll provide in the video description for those of you wanting to rewatch this live stream. And yeah, I mean, thanks for attending this live stream for this second episode of the Build a Bioinformatic Project from Scratch series of a live stream. And I'll see you in the next one. Take care.